So this article by Ron Hicks is titled Programmable Logic Controllers. Industrial control is no longer a relay race. Okay, so I'll begin by reading this little editor's note that he typically puts at the beginning of each article. Here he says, in many ways, this feels like bits from your past. So that phrase is in quotation marks because I guess it's like a reoccurring section in the magazine. He writes, just a few months ago, I watched a pressman cussing the relay panel on his press. Actually, I didn't know it was a relay panel until I looked inside. That box contained a hellish mess of color-coded wires, long ago coded a uniform black, and relays crackling and sparking as they connected and disconnected 220 volts AC. The hearts of these ancient machines aren't the motors or the fancy rollers, they're the relays. The cussed, nasty, grimy, indispensable relays. Read on for more information on new hearts. Alright, that was one of his better introductions to an article. Well, Ron Hicks begins by saying, you may think this article seems out of place in a microcomputer magazine, but it's not. You see, programmable controllers are nothing more than microcomputers interfaced to real-world inputs and outputs. In its simplest form, a programmable controller consists of a central processing unit attached to inputs and outputs. The CPU has a program that tells it to energize or de-energize outputs according to the state of its inputs. Industry uses programmable logic controllers, known as PLCs, for a variety of tasks. You'll find small PLCs built into electronic motor controllers, machine control panels, and even vehicles. They oversee current, draw, speed, and load factors. They monitor limit switches and operator inputs. The typical small PLC will have from 16 to 200 I/O points. Larger PLCs can control whole assembly lines or entire factories, industrial robots, and their support equipment, such as conveyors, tool holders, power units, etc., are all major users of PLCs. Not only do they control equipment, but they also report system faults to the central computer so technicians can be dispatched. Many of these units also log data and generate production or maintenance reports. These larger PLCs typically have 200 to 2,400 I/O points. I almost said ports there. Well, of course, PLCs can be networked via mainframes. This way, any machine or human on the network shares the I/O and data of all the units, and software developed on the mainframe can download to one or more controllers. One of the early marvels of electrical engineering was the relay. Using a relay, an engineer could control electrical processes using logic. Relay logic is nothing more than a hardwired program. You can control the relay that starts the drill motor by another relay that monitors table position. If the table isn't in position, the motor won't start. This approach worked fine until machines started becoming more sophisticated. Imagine using relays to also sense drill speed, part positioning, tool positioning, coolant pump operation, motor overload, and spindle position. Soon the relay panel necessary to operate a machine becomes more complicated than the machine. Where I work, we have panels containing over 500 relays each. I've spent many hours trying to find bad relays by substituting good ones for the suspects. It isn't much fun. And I thought it'd be interesting to just Google the word bad relay and show you guys those image results. And here are some pictures that pop up when I type in relay panel. As computer equipment became cheaper, electrical engineers started replacing relay logic with CPU logic. Many of the early PLCs were based on discrete mini-computers. ModComp was one of the premier names during the first generation of industrial computers. I have one of the early machines complete with 32K of magnetic core memory. In its heyday, this unit sold for $24,000. As microprocessors came on the scene, most manufacturers moved on to the 8080 and later the Z80, and many PLCs still use these chips. The other main chip family used is the Intel 8088 and 8188. These machines fall into the second generation. A problem arose when PLCs replaced relay panels. Plant maintenance personnel and electricians were the main installers and operators of the new technology. It was easy enough to follow the installation drawings since they continued to be standard electrical ladder diagrams. Programming was another thing. Many of the early machines were programmed in Boolean algebraic equations, hardly the forte of the average maintenance mechanic. The obvious answer was to use the already familiar ladder diagrams. Ladder diagram programming, also known as LDP, uses graphic images of contacts and coils representing the familiar relay circuits. With a ladder diagram, an individual line of code is called a rung. So this is a good enough picture of the example he's showing in the magazine. Remember, these magazines are not online, or else I would show them to you. But he writes that the above example shows a normally open contact, which is A, and that's true in this picture, so this is an open contact. A normally closed contact, B, and a coil. In his diagram, it's just a circle. Here they're using like parentheses, but it appears this represents a coil. The contacts can be assigned to real inputs, so an energized input and a non-energized input will cause coil to energize. Coil can be assigned to a real output as a motor starter or other electrical signal. In an LDP program, power always flows from left to right. Although these are examples very simple, LDP programs can have up to 100 elements in each programming screen, and programs may have up to 100 screens. Each PLC's manufacturer has its own proprietary LDP. Some implementations have added features such as subroutines and advanced mathematical features. The best of the LDP languages support a basic-like language composed of keywords that can be used in the same networks as the relay contacts. I've shown an example of an advanced ladder diagram below. I'll make a separate short video showing you his exact drawings from the magazine here. But if we click on some of these pictures, we can easily imagine how quickly this can become complex. In his picture, he has a ladder with some variable-looking letters. For example, TSEC stands for a second timer. There's a conditional statement, a go-to network number. And he did mention many LDPs were proprietary. He goes on to write many different machines are used as programming and control computers. CP/M-based Kpro machines were very popular for a while, as were VAX computers. However, with the popularity of the IBM PC, most companies have switched to the PC standard for their programming and control computers. Many companies make hardened IBM PC AT compatibles for industrial users. They have sealed cases, shock-mounted hard disks, and super heavy-duty power supplies. In dirty or wet environments, they use membrane keyboards. At a recent trade show, one vendor had his AT compatible running in an aquarium with fish swimming around the EGA monitor. So I'll skip over the next few sections where he gets really into the details. The next section is called System Setup, then PLC hardware, digital inputs, output cards, analog inputs, and then of course analog outputs. I will, however, read from this section titled Servo Controller Cards. A servo motor controller is one major PLC use. Servo motors are used for robots, part positioning, machine control, and a plethora of other uses. Servo control consists of two separate functions, sensing motor position and changing motor position. Servo controller cards have an output driver and an input. The encoder reads a motor's spindle position. The LDP program decides where the motor should be. The CPU sends a signal to the output section of the controller, which sends the output to the servo motor. The encoder then verifies the motor's new position. If the motor's shaft hasn't reached the correct position, the controller card detects the error and sends a correction via the output to the motor. This way, the CPU doesn't need to check for proper position. So that's pretty much the end of the article. He does have a conclusion, and then one last section called Computer Jobs in Industry, but I'll skip those. Thanks for watching.